In this video, we're going to explore how the order and the composition of a peptide can influence its individual acid-base properties. So remember, when we're thinking about acid-base chemistry, we're really thinking about the reaction of an acid with water, right, in this equilibrium to form the conjugate base and hydronium, which we know this is governed by Ka. And then for a base reaction, we have our base reacting with water to produce the conjugate acid, and this time hydroxide, and this is the base dissociation reaction, which is governed by Kb. So when we discussed the strength of acids and bases, we talked about it in the context of the stability of the base. The more stable the basic form of an acid is, the more likely it is that we're going to have a high concentration of products. And remember, anytime you have an equilibrium constant, we're thinking about the concentration of the products divided by the concentration of the reactants. So if we can come up with a chemical system or an acid that has a really strong conjugate base, that means that that base is stable, meaning we're going to have a high concentration of the base, therefore we're going to have a large concentration of products. So we have a big product concentration and a small concentration of reactants. So in the situation where we have a stable base, then we have a high concentration of products, meaning we have a large Ka, which corresponds to a small pKa. This is a molecule that's a good acid. The opposite is true if we have a really unstable base. So if we have an unstable base, this means that our Ka is going to grossly favor the concentration of our reactants because our products are not stable. So in this case, our Ka is going to be really small because we have unstable products giving us a large pKa. So this molecule is not as good of an acid. In the past, we've talked about how a stable base can be created if you can draw resonance forms. For example, a carboxylic acid has a conjugate base that has resonance forms, right? So we have this carboxylate where we can draw resonance forms, and that makes it more stable than something that does not have resonance forms. So a carboxylic acid would be a better acid than something like an alcohol, which does not have resonance structure in its basic form. Another way that we can create a stable base is to provide something else to stabilize it. Okay, as we can see here for our carboxylic acids, right? For our carboxylic acids, the basic form has a negative charge. And that's important because if we could bring a positive charge into close proximity with that, then according to Coulomb's law, this would be a favorable interaction. And favorable interactions will help stabilize the anion form of the molecule. So if we had a solution where we have a positive charge in close proximity with our conjugate base, let's say we have a sodium cation present, that's going to stabilize the base, making this base even more stable than it already was. In this situation, we get an even larger concentration of products, making Ka increase even more and decreasing our pKa even more. Okay, so it's all about creating a stable product. So let's think about how this can relate to our amino acids. So in the previous exercise, we discussed two different peptides. The only difference was the order. So one of the peptides we had an alanine, which had a CH3, followed by an aspartic acid, where we had our carboxylate here, and then our lysine, 1, 2, 3, 4, nitrogen, was on this side. We had a valine, followed by another alanine. Okay, we have this peptide compared to the peptide where the valine and the lysine switch positions. So we had our alanine, we have our aspartic acid, we then had the valine, Now we have our lysine. And finally, we have our alanine. So what we can see here is that in our first peptide, we have our lysine and our aspartic acid on opposite sides. So these are really far apart and they won't interact. However, in the peptide where we have the aspartic acid and the lysine on the same side, this actually brings these into nice close proximity. And since these two charged molecules are in close proximity, they help to stabilize each other. So as we talked about above, if we have two charges in close proximity and they're stabilizing each other, then this will stabilize the base form of our carboxylic acid, and it'll stabilize the acid form of our lysine. So this means the base form of the carboxylic acid is going to be more stable. So when we think about our acid dissociation reaction for aspartic acid, then we're going to have a Ka that favors products a lot more, right? So we're going to have a larger concentration of products than reactants. And this means that under these conditions, the pKa for aspartic acid is going to be a lot smaller than we might expect for aspartic acid by itself. And that's because the base form is stabilized, so the products are stabilized. Whereas for lysine, so with lysine here, we know that we have our Ka is equal to, now we're thinking about the ratio of products to reactants. And in this case, our acid form is stabilized. So in this case, we actually are going to have a more stable reactant because the acid in the acid dissociation reaction is a reactant, and we're going to have a small product concentration because it's less stable. So in this case, for lysine, because of the proximity of the carboxylic acid, we're actually going to have a larger pKa. So as you can see, the order of amino acids within a polypeptide chain, or as we'll see later, a protein, can really influence not just the physical properties, but also the chemical properties and the potential for reactivity of the amino acid side chains.